Hi, I want to talk about the topic of quantum uncertainty from Heisenberg's uncertainty principle and the de Broglie wavelength, and trying to apply them to some very ridiculous situations, but also to a situation where they really would be useful. So could quantum uncertainty, or the quantum nature of a major league fastball, explain why catchers sometimes just don't catch pitches? So from de Broglie's wavelength equation, the wavelength of the wave nature of a momentum is equal to Planck's constant h divided by the momentum of an object. So for a major league fastball, we're talking a 0.145 kilogram ball traveling around, say, 41.1 meters per second. That would give us 5.96 kilogram meters per second of momentum. 6.626 times 10 to the negative 34 joule seconds divided by 5.96 kilogram meters per second is a wavelength of about 1.1 times 10 to the negative 34 meters. So, no, that is more than 1 trillion times smaller than the structure of everyday material. So that wave nature does not come into play with the momentum of that object. That is what we would call a strictly classical object. Now, in terms of quantum uncertainty, Heisenberg's uncertainty principle says if we take the uncertainty in position and multiply by the uncertainty in momentum, it has to be greater than or equal to Planck's constant divided by 2 pi, then divided by 2, and what we call h bar over 2. Well, your ability to gauge the momentum of a ball is probably going to be sort of, if it's pretty good, at plus or minus 0.01 kilogram meters per second. So to translate that into an uncertainty in position, I take Planck's constant, divide by 2 pi, divide that by 4 times, not my momentum itself, the uncertainty in my momentum. And if I divide by the uncertainty in my momentum, I get an uncertainty in position that's limited to 5.3 times 10 to the negative 33 meters. So again, at a typical ability to assess the momentum of a baseball, you would be limited in assessing its position to smaller than the location of an atom. So it's not quantum uncertainty, it's human reaction time, human reflexes, processing delays going on there that keeps that from happening. Now, on the other hand, when we talk electrons, so electrons tend to be moving around sort of in orbit in atoms relativistically. So let's say that we have an electron that happens to be traveling at 99.4% of the speed of light. So at 99.4% of the speed of light, that electron would have a Lorentz factor gamma that's equal to 9.14. So for relativistic momentum, the relativistic momentum is gamma times the classical momentum, the mass times the velocity. So if I multiply 9.14 times the mass of an electron, 9.11 times 10 to the negative 31 kilograms, times 0.994 times the speed of light, about 3 times 10 to the 8 meters per second, I get a relativistic momentum of 2.48 times 10 to the negative 21 kilogram meters per second. So the wavelength associated with that momentum would be Planck's constant over the momentum. That would be 2.7 times 10 to the negative 13 meters. So a relativistically moving electron would have wave nature with wavelengths on the order of the size of nucleons. So this is something where we would see quantum behavior, we would see quantum interactions happening. Thanks for watching.